Hello everyone, we are Team 200Y, and this season we have worked hard and are continuing to work hard to create the most consistent and effective programming skills run possible. We have used many different algorithms and sensors to keep track of everything that is happening to our robot. Our end goal for this season is to design a programming skills run that has a perfect score.
The first vital piece of our programming is our custom odometry algorithm.
Type of dead reckoning algorithm, which means based on how it's moved, the robot tracks its position relative to its starting position. We use a Cartesian grid to represent the field. Our version of odometry uses two free-spinning tracking wheels, an inertial sensor, and a coded algorithm. Sometimes there is slight drift on the inertial sensor, so we use a custom filtration function.
Every 10 milliseconds we take measurements from our sensors and use trigonometry to figure out how far a robot has moved on the field.
On our robot, we use one V5 vision sensor and ultrasonic sensors for ball control. In the future, we plan on using the optical sensor, potentiometers, and another vision sensor.
Delving deeper, we use the V5 vision sensor to develop another one of our programming annotations, the ball alignment function. After attempting to use our odometry algorithm to position ourselves, we realized that the balls wouldn't always be in the exact same position, so we needed another solution. We decided to use the V5 vision sensor to see the ball's position relative to the robot. The robot strafes and corrects its angle until the ball is aligned with the camera. Looking ahead, we would also like to use a similar theory to align our robot with the green backboard on the towers, which would allow the robot to score balls more accurately. Moving on to the optical and ultrasonic sensors now, one of the most important aspects of controlling balls in the intake is knowing when they are about to be scored. Currently, we are using the ultrasonic sensor to see when there is a ball higher up in our intake. This allows us to write functions such as our score macro, void macro, and intake to the ultrasonic sensor macro with much greater accuracy. We plan to change our ultrasonic sensor to an optical sensor once there is a supported library in Perez. The optical sensor will be a big upgrade because it will allow us to automatically sort our red and blue balls as they come into the intake. The optical sensor will allow us to check that our balls have successfully been intaked or hoarded using the gesture detection.
Final sensors we plan to use this season are two potentiometers on our conveyor deploys. These will allow us to know when our robot has successfully deployed because as the axle rotates, the values will change. We will also know when the robot has successfully intaked a ball, because as a ball goes through the conveyors, they open slightly. When the potentiometer senses this opening, we will know that a ball has been intaked. Another way we make our programming skills more efficient is multi-threading. During our skills run, we use multi-threading to manage the balls in the intake effectively while the base is running. Without multi-threading, we would start the motors before we started moving and stop them after because the movement loop blocks other code. This year, however, we've employed the use of multi-threading, which gives us control over the sensor and the motors in our intake while our drivetrain is running in a separate task. Throughout our programming skills, we run our macros as described earlier in a separate task.
Now that we've spoken in depth about our robot and sensors, we want to talk about our end goal for this season. We've been working on an algorithm that allows us to generate an entire skills run through code. In our code, we have a class that keeps track of everything on the field. We also have a class that stores the characteristics of a movement. For example, whether the ball's going to pick up or score a ball, and the end position of the movement. Following this, it determines what series of macros it needs to run to complete its goal. Next, we have a root object which stores a list of movements. In the root object, the robot figures out how many balls it needs to obtain before going to each tower, and then finds a set of efficient movements to gather those balls. It proceeds to drive to the tower and scores/descores all the necessary balls. This process is repeated for all 9 towers on the field. Due to the complexity of this project, we've only just started testing with our robot. However, so far, we have successfully gotten the robot to generate and describe a route. The generated route has been traced on this image. Now that we've talked about all the current and planned programming features, we will now show off our uncut 75-point programming skills. It does 7 towers and scores 9 balls.